This is my little fire brigade analogy with a series circuit where the houses are beside each other. The water comes from the water source. A little bit of water goes on the first house. The rest of the water goes on the second house. Goes return back. This is a series circuit. Let's just take a look at a parallel circuit and let's see the differences a little bit. So let me just go ahead and take a second and sketch everything in, and then we'll get caught up to speed as to what I've drawn. Okay, so what I attempted to show here were two houses, this time not side by side, but let's say they're across the street from each other. The pond is down the road. The pond is just as far from one of the house as it is the other house. And so the person here, the first person here, has a bucket, and we fill up our bucket with water, and he passes it down, and it gets along here, and at one point the person, and let's say this person right here, person number 4, has the choice. Person number 4 can pass that bucket over, and we can put out the fire at house number 1, or we could put out the fire at house number 2. And person number 4 might make the determination that the house fire at number 2 is a little bit bigger than the house fire at number 1. And so it's not that we're going to ignore the fire at house number 1. We're going to send most of our water down to house number 2. Most of the water. And then we're going to send some of the water to house number 1. So we're going to take care of both fires at the same time. We're just not, since fire number 2 is bigger, we're going to try and put more water on that one. But they're going to try to address both fires at the same time. Again, back to my analogy. The people are the electrons. The bucket is the charge. The water, the amount of water in the bucket is the energy. The fire represents the load or the resistor, the object that needs the energy. The fire needs the water to put it out. The resistor needs the energy to make what. And so let's look at it, and let's just say that through this entire process, they are able to get out 5 buckets every minute. So the first part of the line, they're passing 5 buckets every minute. And they've decided that there's going to be 3 buckets every minute. Once it gets to person number 4, that they pass 3 every minute. They pass 3 of these buckets over to house number 1, which means 2 buckets per minute is going to house number 2 buckets per minute is going to house number 1. I think I misspoke earlier with 3 buckets a minute going to house number 2. And so they're going to divvy up the water this way. So many buckets of water are going to each house every minute. Well, I talked about that the current I is how fast the buckets are moving. And what this tells me is that my total current of 5 buckets per minute is being split up between the current to house number 1 and the current, or the number of buckets per minute, to house number 2. If every bucket is full of water, so every bucket has 1 gallon of water, this 1 gallon of water is going to be used somewhere. It's all going to be used. 1 gallon is going to be thrown on house number 1, or the entire bucket is going to be thrown on house number 2. And remember, what I had mentioned earlier was voltage. The amount of voltage is how much the water level changes. And so if we dump the entire bucket of water on the house, we're putting the entire amount of voltage that we get from the pond onto that house. The voltage is the change in the water level. And if the water level, if we have a full bucket of water here, we're going to use it either at house number 1 or house number 2. What this means, whatever voltage we leave at the battery with, that's the voltage of the battery. That's how much water is in the bucket when it leaves the pond. That same amount, the entire bucket amount, is going to be thrown on house number 1, and it's going to be thrown on house number 2. And this is one of the characteristics of a parallel circuit. It has the same voltage drop across each branch, because in a parallel circuit, it's leaving. Here's one branch, here's the other branch, and that's what's in with our split. Here's our split. That's what makes our parallel circuit. That's what defines that parallel circuit, this split. So whenever we see this split in the line, that ought to tell us right away, parallel, parallel, parallel. That's a very key indicator. In a parallel circuit, the voltages across each branch are the same. In a parallel circuit, all the currents add up to the total current. I think what I want to do is take a quick look and apply Ohm's law to that statement with the current and see what happens. And remember, Ohm's law, V equals IR, if I rewrite that, that's I is equal to V over R. So let me rewrite this expression with the current in terms of Ohm's law, and my total current would just be my total voltage is over my total resistance is equal to V1 over R1 plus V2 over R2. And if we take advantage of that all my voltages are the same, and I rewrite this expression as simply V over RT is equal to V over R1 plus V over R2, I see that my voltages can simply cancel out. And what this leaves me with is a way to calculate the total, or some people call it the equivalent resistance, with resistors in parallel. And that expression is it's a lot more complicated than just simply adding them up, but it's not too bad.